Okay, so the next one is a series motor, and it is rated for 200 volts, 7.5 horsepower. So remember what the ratings mean, right? The 200 volts is ES, 7.5 horsepower is the rated mechanical output power that it should produce if operated at full load. Armature resistance, 0.8 ohms. The series winding resistance here, you notice, given to you separately from the armature resistance, 0.15 ohms. We're told at full load, so that means at 7.5 horsepower output. The armature induced voltage is 160 volts. Okay, so remember, induced voltage is E0. That one goes on the armature. The 200 volts ES goes over by the source. So, again, let's think about drawing the equivalent circuit. So, I'm going to pull it in. So hopefully this is going to work the same way it did before. I'm going to copy that. I'm going to go back to the question with the page with the question on it and paste it. And then I can resize it. Not going to let me grab it. Okay, let's try that again. Okay, so hopefully we'll be able to go a little bit faster with this one. We'll see how it goes. Now here's our motor, and so you notice that this symbol here represents the shaft, and you'll see them on some of my diagrams. If I was drawing them on the blackboard or the chalkboard, I'll probably include it on them all. So our P out, our rated 7.5 horsepower, our armature resistance. This time we're showing a series resistance. We don't bother with a rheostat with series motor circuits. Our E0 was given to us at 160. Our source voltage, remember the rating is ES, and it goes over here on the source, 200 volts. Normal cases, this voltage right here got to be bigger than E0, right? The standard for E0 to be less than ES because there's a voltage drop across RA, so that makes sense, hopefully. Okay, so now this says armature current and input power. So remember armature current. Armature current is our equation, E0 is equal to ES subtract IA times RA solved for IA. And so we should get IA is equal to the voltage drop across the armature circuit, which is the difference between ES and E0. And so, you might be able to do that without the calculator, divided by the armature resistance. And so here we have 40 volts dropped across the armature because it is 200 volts subtract 160 volts divided by, now let's think about this one. I wrote this equation down because I'm so used to doing a shunt motor. And here the armature circuit resistance is given to us in two pieces, and so we can't forget to say that IA goes through these two resistors, RA plus RC, and so it is the sum of those two resistors. And so down here we need to include RA plus RSE, and it's very important to do that for the series motor and the compound motor. And so we have then here at 0.8 ohms plus the 0.15 ohms for the series field resistance. And so that was A over there, we should have said. And now that's equal to 40 volts divided by 0.95 ohms. And so remember now that the voltage drop is 40, not either one of these numbers by itself, the difference between them. So it's very common to put one of these numbers over some of that resistance, and then you got an incorrect calculation. And so remember that. Now, so 40 volts over 0.95 ohms, and that gives us 42.1 amps. So 42.1 amps for armature current. Now, in this one, right, there's only one current. It's a series circuit, and so that is equal to I line as well. We might want to note, because you know, in this one, well, we could say that P in equals IA times E source, I suppose. But normally when we calculate the input power, you know, our standard equation is going to be I line times ES. And so it's important for us to realize that with the absence of a field current, IA is I line. And I'll say absence of a field current, I mean a shunt field current, right? And so we have, I could have said ES times I line, but it don't matter what order we put them in, right? 42.1 amps multiplied by the 200 volts, and P in has a value of 8,420 watts. Okay, so we go with that. Now, if I move up here next to the circuit then, for part B, we are asked to find the total of the copper losses. So remember now then that we don't need to find them individually. So the copper loss is going to be equal to, let's call it IA squared times R. And we don't need to get them individually. And so we have now, so we're getting close to the end of class. I understand that you guys, if you got somewhere else to be, you're going to have to leave. But I'm going to continue on with that example for those who want to stick around. And the recording of this lecture will be available, and a bit later I'm going to publish those examples as MP4, so you can review it then if you gotta go. Okay. Now, and so we have our current at 42.1 amps. Well, yeah, but yeah, more so the way that I worded the question, because I asked for the total. Yes. So, and so sometimes I ask for losses in each winding, and then I expect you to do them individually. And so here, the calculation is a little bit easier to find the total, because, well, that's what we're asked for. If you found them individually, I'd expect you to give me a sum anyway, right? And so All depends on how I worded the question, really. Now, so if we got then the 42.1 amps squared, and we're going to multiply that by the 0.95 ohms, that comes out to 1684 watts. And so that is the total of the copper loss. Okay, so now part C was PMI, and in this one we've been given E0, and we've calculated IA. So PMI should be relatively quick, and the idea now is, remember that PMI is equal to P in, which we got, minus the copper loss, which we got. So we don't really need to do the calculation of E0 times IA. We can take the difference between those two values, right? And so E0 times IA gives us 160 volts multiplied by the 42.1 amps, and that means that PMI has a value of 6,734 watts. And again, you know, you keep 3 or 4 significant digits. No matter what way you does that, you should come out to be pretty well exact, right? You might have some rounding error, but if you're using 2 significant digits, you have some rounding error. Right now, you might not, right? And so PMI is equal to P in, subtract the copper loss, and so if we went with 8420, subtract the 1684, you're coming up again with exactly 6734. And so remember, you know, there's always 2 ways to get through a lot of these calculations. And I put amps up there. You notice that, I suppose. Here I'll put in amps, right? But of course that should be watts. And at least I can erase it relatively easily. So watts it is. And so don't matter how you do that calculation, you should come up with really close answer. Okay, part D now is the constant loss, and so I'll scroll down a little bit, and let's see if I can put part D right here. And the constant loss now is PMI subtract P out. And so we take P out, and we know now that it's operating at full load. So that rated power should be the power out, and it was 7.5 horsepower. And convert that to watts, which simply means multiply by 746. 746. Oh wait, left out 6. Yeah, okay, let's get 746. I've done very good job there, watts in 1 horsepower. And so that power out, a bit less than the last one that was rated at 10, right? And so 5,595 watts. And so the constant loss, again, remember, is the mechanical loss. And so I'll write that as CL is equal to PMI subtract P out, and we have, if I can squeeze it in here, 6734 subtract the 5595. I thought I was going to get better at this as the class went on, but my wrists and shoulder are starting to get painful now. That stuff happens when you get old, right? Like me. Let's see, my cursor is here now, yeah. And so that copper loss then, or that constant loss rather, came out to be 1141 watts. Okay, now last part of this is the efficiency. And we have our value for P out and P in. So the efficiency then should be a relatively easy one. I'm going to switch over to red now. Part E, I'll put it right here. And efficiency then is equal to P out over P in. And remember then that gives it as a decimal. So multiply that by your 100 to convert 2%. And our P out was the 5,595 watts. That represents the 7.5 horsepower. And the power in, we calculated it at the beginning as 8,420 watts. And so if I do that and multiply by 100, I came up with, if I round it to 3 significant digits, 66.5% for efficiency. Any questions on that? Okay, so see a few of you are still remaining there. Sorry to keep you over. I won't do it every day, but no. And so I'm going to turn off that recording now, and I will save that as an